Let's talk about ultradistributions. So more precisely, what I'm describing here is called homogeneous ultradistributions in the post, but we won't really care about non-homogeneous, so we should be calling those ultradistributions. So we started with, before we had this thing where in infra-Bayesianism we describe beliefs using credal sets, but I said that this is just the simplest case. There's also more general objects that are sometimes useful. And this is going to be a certain type of more general object. So first of all, to motivate it a little bit, just kind of very rough motivation, recall that we had box X was closed convex subsets of delta X. So one thing which notice there is that the empty set is also a closed convex subset of delta X. But this is kind of a strange one, right? If you kind of imagine the space of those convex subsets, then there is this disconnected point, which is the empty set, and then there is everything else. So this is a little weird. Also, the one natural operation on those things is taking intersection. Right? If you have like theta and psi are elements of box X, then theta intersect psi is also an element of box X. And in some sense, we can think about it as kind of a logical, conjunction. Mm-hmm. And then we also have like, the convex hull of those two things. And this is sort of a logical disjunction. So those credal sets actually form a lattice. And in particular, just subset of X, right, that's kind of naturally embedded into box X. This is what's called a sharp credal sets. Right? If I have some subset A, then here I can consider a subset of X, then here I can consider the set of all distributions or support lies in A. And for those type of credal sets, this operation corresponds to taking intersection and union of the sets. So when we look at it this way, it feels like credal sets are in some sense a synthesis of probabilistic representation of knowledge and logical representation of knowledge. Like when we're doing this with logic, like specific model theory, then we kind of represent knowledge as sets. Or in some sense, like intersection union sets corresponds to kind of logical and then more. But to know something means that to know that like the world lies in a particular subset of the ways it could be. And in probability theory, we represent knowledge in a different way. And here, it is kind of a representation of knowledge that generalizes both at the same time. So from this point of view, the weirdness thing here is that this lattice is non-distributive. And in this sense, it's kind of very different from the lattice of subsets. But from this point of view, the empty credal set, it kind of corresponds to the logical contradiction, right? It kind of corresponds to false, the empty set. Something that cannot ever be. Okay, so now let's again focus on this thing for a second. Let's look at this. So this operation, it also has an annoying property that it's discontinuous. If I have like two credal sets, And I have like, let's read it this out. There's the sound. Two credal spheres that I'm intersecting. Right? And they intersect over here. But now I'm moving them apart. Now they intersect at a single point, maybe. And now I move them apart even more. But you don't intersect at all. So the intersection kind of suddenly jumps from being a point to being an empty set. So those continuously. So this I'm just trying to give you some intuitive sense that something about credal sets is there's something inelegant about the fact that this kind of empty set is this disconnected point. So there's like a more general object where you don't have this. And let's see. And this is the ultradistributions. So first of all, let's do some notation. First of all, contributions. So a contribution on X is just a measure theta on X such that theta of X is smaller or equal to 1. Okay? And we denote delta Cx in space of all contributions. So notice this delta Cx has partial order. Right? What does it mean for one contribution to the smaller equal than the other? Just the obvious thing is that they're literally for every right to the list. Theta 1 is smaller equal than theta 2 when for any measurable subset we have theta 1 A smaller equal than theta 2. Okay. So now an ultra contribution on X is theta capital, a subset of delta Cx such that 1, 0 is intercept, 2, the set is closed, 3, the set is convex, 4, the set is downwards closed. So for example, if X is a 2-point space, then we can kind of visualize this by thinking of there's the measure of one point, there's the measure of the second point, and their sum has to be, and for contributions, their sum has to be at most 1. And now we have some subset in here, which is closed, convex, and downwards closed. At any point, this rectangle is also in subset. That's like this. And we can also define an ultradistribution on X is that distribution such that its intersection with delta x is not empty.
I think that's slightly stronger.
What is stronger than what?
Oh, I mean, so the definition of ultradistribution that I remember is something like it's the downwards closure of a closed convex subset of delta x. That is strictly stronger than the thing you wrote on the board.
The thing I wrote is the thing I wanted to write.
Okay, because you can have take some closed convex subset of delta x, downwards close it, and then adjoin an extra contribution, and you will end up with something that fulfills your board definition, but that cannot just be expressed via its restriction to delta x.
Yeah, it's not a crisp ultracontribution.
Okay. Alright. Oops.
Okay. So this means that like this, for example, would not be an ultradistribution, but this, if it touches this thing, then this is not a distribution, right? Okay. And now,
Sorry, what's downwards close?
so downwards
So there's a
close.
partial order on the space of contributions, and downwards closed just means if x is below y and y is in the set, then x must be in the set too.
Yes.
Okay.
So you picture everything like
Okay, the subtree root that. Yeah, I get it.
so you could have something that's just like a disk in the middle of the triangle. So then needs to include everything that's to the left and below it. too.
Shouldn't that be theta instead of theta prime for in delta c of x?
For any theta in theta capital, theta
Oh,
prime
alright,
is
yep.
to effect.
Okay, yep,
If theta prime is smaller equal than
Alright,
theta,
yep.
if theta prime is closer to theta.
Alright.
Okay.
And sorry, what was the example here for an ultra-distribution and not ultra-distribution?
Again, what's the question?
So you had two examples, one of them an ultra-distribution and the other doesn't.
This is an ultra-contribution, which is not an ultra-distribution, and this is an ultra-distribution. We can denote like box Cx is all ultra-contributions on X, and box Dx will be all ultra-distributions. So, given some function, given some continuous function on X, and an ultra contribution, so expectation with respect to theta of f is defined to be the maximum over theta small and theta capital on the expectation with respect to theta small. Where by this I just mean the integral of f times theta. Forgive me for the slight hasty documentation where the expectations with respect to something is not appropriate. So notice that the word ultra here is instead of infra. This is because we're doing here, this is related to the fact that we're doing here maximum instead of minimum. And the reason we're doing it is because the functions we plug in here are going to be loss functions instead of utility functions. And you could kind of define those things with utility functions, but it would be uglier. So maybe to make it all less confusing, I should have done all of those lectures with loss functions instead of utility functions the whole time. Then you would be less confused now. But if you try to pretend that I was all the time talking about loss functions instead of utility functions, at the same time, same thing with the minus sign, then this is just the usual thing we have then this will be the usual thing we have in the credal set. Okay. And notice the credal sets are naturally embedded into ultra distributions by the operation of downwards quotient. Right, so if we have here some psi credal set, then here we can write psi hat, which is just theta of theta in delta cx, such that there exists some theta prime in psi with theta lines below theta prime. Well, yeah, M0. Do you want this definition to be correct for the anti-credal set? Yeah. Okay, so credal sets are a special case of non-credal. This gives us some kind of an even more general uncertainty than we have in credal sets. And one way to see that there's something, one nice thing about it is that now, if before we had this anti-credal set, which was a disconnected point, now this entire space is connected, right? Because inside of, actually this is not true, this is C here. So non-empty sets map onto D, but the empty set becomes to 0, right? So this thing is like connected, and like 0 is kind of, there's like a continuous way to interpolate between 0, which is like the logical contradiction, and something which is just a distribution of some non-empty credal set. And also, if you intersect things, then at least with respect to, it's not actually true in the MIP topology, but at least in some topologies, it would be continuous. Or like for a finite set, at least it would be continuous. Because, like, if you have two probability intervals here, they're kind of mapped to ultradistributions that look like this. Right, and the second one, let's see here, so there's another interval. So this corresponds to something like this. Right, so now when you intersect them and you move them apart, the intersection doesn't jump discontinuously. Just at some point, at some point those intervals no longer. So you have like some interval like this. And some intervals, I can switch them around here in the picture, something like that. Some intervals like this. So their intersection is still this rectangle here, right? This rectangle here. So it doesn't, when the intervals stop intersecting, the ultracontribution doesn't jump. It just keeps changing continuously. It just stops being an ultradistribution. Right? So how do we do infra-Bayesianism with ultradistributions? Well, the first approximation, everything is the same. There, all the definitions I had before, we could kind of repeat them. There is one difference, which is, okay, so let's explain what the difference is. So recall that previously we had like we had this notion of an environment, which is a mapping from history to distributions over observations, right? So now we're going to need a thing which, not sure about the terminology, but let's call it semi-environment for now. So in many papers you will see semi-distribution, something like that. So let's call it the semi-environment, for lack of better name, would be U. Okay? So now the probabilities don't sum to 1 anymore. It's like something that can kind of fizzle out. The environment can just decide to stop and disappear.
Is it delta C rather than box C?
Yeah.
Okay.
It's just the same environment. It's not like a wall. It's an environment. No. So, but those things, they're kind of very similar to environments in the sense that, if you have a semi-environment mu, so if we have like semi-environment mu plus some policy pi, then we can build mu pi, which will be an element of delta C A times O. Okay, so the same environment can interact with the policy. There is some probability the world will explode, some probability it won't explode, and then if it doesn't explode, we get a destiny, like an infinite sequence of actions and solutions. But if it explodes, then it exploded, so we have like a contribution of the destinies. Okay. And now we can define what is need to have this. I need to. So pretend that the thing we defined previously was actually called a crisp law. And now we define a general law, okay? So we had a definition of law before. The thing called law is actually what's, in the more general context, is called a crisp law. So now we have a not necessarily crisp law. It's like going from, commutative algebras to non-commutative algebras. So non-crisp law is lambda from the space of policies to box you could put here C or D. It's likely, so let's say it's D here, but you could also consider what happens if you put C here. But let's stick with D. Such that, maybe if it's C, we should call it a sand law, I guess. terminology, such that there exists in a set of semi-environments such that for all I in phi, lambda phi is the set of u pi for u. Okay. If you remember the definition of law from before, this is the same. What are the differences? That here we added this d to the box, and here we do same environments instead of environments. Okay? Makes sense? Now, all the definitions of optimal policy and learning and blah 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 blah, this is all the same, except that we need to write everything with loss functions and not utility functions to come out, right? But I won't repeat it because this is literally like the same definition. After some. Okay, so we created an even more general type of infra-Bayesianism than we had before. And now it's time to reap the benefits. So now I claim with this more general type of infra-Bayesianism. So first of all, why could we even possibly want a more general type of infra-Bayesianism? Because the notion of learning produces a more general type of desiderata, right? Like previously the desiderata we could, so like the framework of infra-Bayesianism is there because, or mostly because, we want to look for learning algorithms. It gives us a certain target. What is the thing where we want to have? The thing we want to have is like learning algorithms, statistically and computationally efficient learning algorithms, right? And what is a learning algorithm? It's something that satisfies this particular desiderata. So previously we defined desiderata with this credal set, which kind of means that we have like, this kind of hypothesis about the world that is true for some environments, not true for other environments. And if we happen to be in an environment in which the hypothesis is actually true, then our algorithm is guaranteed to converge to certain loss. Right? This is what happened with information. Or maybe I should have actually emphasized this point more in hindsight. But like the criteria that the regret, the infra-regret goes to 0 for a certain law, right? So that's maybe I should write this down. Before we talked about this important criterion that the regret of some policy with respect to some law as goes to 0 as gamma goes to 1. Right? This was like our definition of what it means to learn some hypothesis. Right? But what does it actually mean? So the regret of phi with respect to lambda, we could also kind of rewrite it as we could kind of rewrite it as a maximum over all environments which are compatible with lambda of the regret of phi mu gamma. Okay, so what does it mean for an environment? What do I mean by this notation? So mu receive lambda, it means that for all policies pi, mu pi is an element of lambda plot. Okay? So basically any law defines a set of environments. So if you remember, I said that we could have just defined the law as a closed convex set of environments, but that definition would be somewhat redundant because there would be different sets that define the same law. But on the other hand, if there's a law, there is a canonical way to get a set of environments. Which is just all environments which satisfy this condition. All right? So now there is a property which is just obvious from the definitions, that the regret of a policy with respect to a law is the worst case, the maximal regret you could get with respect to all environments inside of this law. Right. So in other words, you should think of a law as some hypothesis that may hold for some environments and not other environments. And then saying that the regret goes to zero is like saying that for all of those environments that satisfy the hypothesis, we can kind of bound the regret. But this thing here was very crisp in the sense that an environment either satisfies the hypothesis or not satisfies the hypothesis. There is no a little bit satisfies kind of ish the hypothesis, right? So what those things buy us is that they allow us to define, it's kind of really similar to fuzzy sets, you know, fuzzy sets. Fuzzy sets where instead of element being in the set or not in the set, there's how in the set it is. So those kind of ultra distributions, they allow us to build laws where, like, the law imposes something. It like having the low regret with respect to this law requires the policy to. It gives like a stronger requirement on some environments than other. Like there are environments which are kind of very deep inside the. So kind of if you want to just think kind of geometrically, right? Then you have like a thing like that. Then kind of this kind of distribution is like very inside this, but this is kind of farther out. And like in some sense, what you get is like as the environment is more and more far from this ultra distribution, then kind of the desideratum implies something stronger, weaker correspondingly. So it's kind of this fuzzy criteria, it's kind of fuzzy hypothesis, which doesn't just hold for some environments and doesn't hold for other environments, but for some environments it holds, for full environments it's kind of ish holds, and then like, you know, if your policy has to like obey low regret for this hypothesis, then it doesn't have to be really good, but it has to be kind of okay for this environment. This is kind of intuitively what happens.